Welcome to Lecture 2.2, Vectorization for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what vectorization is, why vectorization might be useful for engineering problems, how to write vectorized array operations in MATLAB, and how to upgrade the dot product function from the previous lecture into a vectorized form. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. To illustrate the concept of vectorization, let's consider a real-world scenario that reflects what we are going to discuss. You and some friends plan a cookout grilling hot dogs. You could grill a single hot dog at a time, but then some people receive their food before others. If you instead put the entire pack of hot dogs on the grill simultaneously, then more people will get their food together. This can be considered as a vectorized cooking operation. The processor, or you in this scenario, accessed the entire quote-unquote array, or the pack of hot dogs here, and applied the function cook to the array as a whole. So the definition of vectorization for our purposes is as follows. Vectorized code is characterized by one instruction, one line of code that operates on multiple data points together. By utilizing vectorized operations, it is possible to write faster, more reliable code while also making it more readable. Disclaimer, this lecture does blur the line a little bit between vectorization and parallelization. Later lectures will introduce parallelization, at which point we can discuss the differences in more detail. But for now, it is sufficient to just say that they are in fact different. If you're interested in learning more about the difference now, the hyperlink at the bottom of this slide provides a relatively thorough comparison between the two. To understand the power of writing vectorized code, it is necessary to first examine the alternative, loops. Later lectures will cover loops in more detail, but it is useful to define them now for comparison's sake. The definition of a loop is as follows. The program executes one or more operations repeatedly until a termination condition is met. If we go back to our example with hot dogs, cooking each one individually is a looping process. The code for a loop might look as follows. First, we define an array of 8 hot dogs. Then we set the loop up with the for and end keywords. And then we specify the length of the loop. This provides the termination condition. We instruct the computer to declare the hot dog index equal to 1, and then to increment upwards until it reaches a value of 8. And then with each increment, we cook the hot dog labeled that number in the pack individually. The variable hot dog index is used to specify which hot dog is pulled out of the pack with each iteration. Again, this code executes the function cook on each hot dog one at a time. In plain English, this code reads as follows. For each hot dog in the pack, numbered 1 to 8, cook each one before beginning to cook the next. For comparison, vectorized code may look something like this. Again, we first define an array of 8 hot dogs representing the pack. Then we just simply apply the cook function to the entire array of hot dogs. For this example, the vectorized operation is only one line, and it's probably also faster. Vectorized code is often easier to read because it is shorter and it more closely matches plain English. To illustrate this better, let's develop an experiment to showcase the difference between vectorization and looping. Our experiment is to multiply 1 million random numbers by 2. To start, we need a function that generates an n by 1 array of random values given a length as its input. We define an anonymous function to represent this operation in the variable random number array with the input num values. That represents the length. The rand function then automatically generates an array of random values given desired dimensions. We specify num values in the first argument as the number of rows and 1 for the number of columns because we want an m by 1 vector. Each element of an array can be multiplied in a loop as follows. First, we define the array for 1 million initial values using the function that we just defined. Then we initialize an array for the output values. Here we use the zeros command to create an array that is filled entirely with zeros. Its argument is a 1 by 2 array, in this case provided by the size command acting on the initial values array. This way the output values array is the same size as the initial values one. Then we outline the structure of the for loop where the index I ranges from 1 to the number of values in the array, which we decided would be 1 million at the beginning. And finally, the code itself is written in the middle. We access the ith element of the initial values array using parentheses, and we multiply it by 2. The result is stored in the ith location in the output values array. Note that the array output values is initialized before the loop. It is possible, but much slower, to skip this step. The vectorized version of this operation is significantly simpler. Again, we define an array of 1 million random values, and then we can, in one line, define the array of output values as 2 times the initial values. Note that because we are no longer accessing each index individually, there is no need to initialize the output array before the operation. Instead, it's initialized at the same time as performing the operation itself. The very last piece to complete the test is to wrap a timer around the code. In MATLAB, the tick command is used to start a timer and the talk command ends it. Declaring a variable timer start with the tick command begins that timer. Then we'd have some arbitrary code in the middle, followed up with the talk command, which takes the timer start variable as an input. With this structure, the variable total time stores the time elapsed between the initialization of the variable timer start and when it was ended by the talk command. We now have all the necessary pieces to put together an actual experiment. Putting the pieces together, we start by again defining the array of 1 million random numbers. Then we have to define the output array, again using the zeros command. Then we start the timer using the tick command, storing it in the variable MATLAB for loop timer. Then we outline the for loop with our bounds for the index going from 1 to the number of values in the array, which is 1 million in this case. And then the body of the loop is written by multiplying each element of the array by 2 and storing it in the corresponding element in the output array. And finally, we close the timer using the talk command and store the elapsed time in the variable MATLAB for loop time. The total time elapsed to multiply 1 million elements by 2 using a for loop is 1.5195 e to the minus 2 seconds, or in other words, about 15 milliseconds. Let's see how this compares to a vectorized version. Again, we start out by defining an array of 1 million random numbers. Then we start a timer using the tick command, and this is the same. Then we multiply the entire array by 2 using the vectorized multiplication operator period asterisk. And then we close the timer using the talk command, and that's it. This time, it takes 5.76 e to the minus 4 seconds, or in other words, about 0.58 milliseconds. As a refresher, the for loop took about 15 milliseconds, and the vectorized code took about 0.58 milliseconds. For this example, vectorization is about 26 times faster. MATLAB has specific syntax for writing vectorized operations. The hyperlink at the top of this page directs to the MathWorks documentation on vectorization. Their rules are as follows. The plus and minus operators do not require any modification, but the asterisk, backslash, and caret operators require the addition of a preceding period to indicate that it should be vectorized. For example, adding the vectors u and v with the plus operator is equivalent to adding the first elements of both arrays, and then adding the second element of both arrays, etc. Subtracting the u and v with the minus operator is much the same, just with subtraction. Multiplication, though, requires the preceding period, so the operator reads as period asterisk to denote a vectorized multiplication operation. The same is true for division, where the vectorized operator is period backslash, and exponents, where the vectorized operator is period caret. Knowing the basics, we can build upon the dot product anonymous function written in the previous lecture. The old function was hard-coded to multiply all three corresponding component pairs and then add them together. Element-wise multiplication like this is easily replaced by the vectorized operation between the arrays v1 and v2. Doing this will return another vector that contains the results of each element-wise multiplication. So v1 period v2 is equal to v1 times v2 1, etc. To return the dot product from this, the sum command can be applied to add each component of this new vector together. Thus far, though, the inputs to this function have been 1 by 3 vectors. We can expand that to accommodate solving for m dot products simultaneously by passing v1 and v2 as m by 3 arrays, where each row represents a distinct vector. For example, consider the following two inputs. First, we define v1 as a 2 by 3 array, where the first vector that's stored is the first row, 1, 2, 3, and the second vector is stored in the second row, 4, 5, 6. Note that while the comma is used to separate elements within a row, the semicolon is used to begin a new row. Then we define v2 as a second 2 by 3 array where the first vector is the first row, 6, 5, 4, and the second vector is the second row, 3, 2, 1. Axial components of each array can then be extracted from v1 and v2 as m by 1 vectors. In this example, we see that extracting the x components of v1 returns a 2 by 1 vector 1 semicolon 4. The y components return 2 semicolon 5, and the z components return 3 semicolon 6. Note that the colon inside of the parentheses is used to access the entirety of the array along that dimension. In this case, the colon is in position 1 inside of the parentheses, and it is therefore referring to extracting every row of v1. The index in position 2 is used to specify which column to extract. At this point, the component-wise multiplication in the dot product can be vectorized as follows. The dot product anonymous function still takes v1 and v2 as inputs, but recall now that both v1 and v2 contain m 1 by 3 vectors, so multiplying the x components together now requires extracting that column and performing element-wise multiplication. Then we do the same for the y components using the index 2 in the column location. And finally, we do the same for z components with the index 3. And all three of those vectors are then added together. This mirrors the original form of the dot product function, which was written in the previous lecture. This can still be improved, though, with even further vectorized multiplication. v1 and v2 are both m by 3 arrays, so the operation v1 period asterisk v2 returns a m by 3 array as well. This arises from element-wise multiplication between each element. The first column is the multiplication of all x components. The second column is the multiplication of all y components, and the third column is the multiplication of all z components. The sum command can be used to condense this m by 3 array into an m by 1 array that represents the dot product of every 1 by 3 pair. This is done using the sum command along each row. Regarding this, the sum command does take a second argument, which specifies the dimension along which to add elements. The sum documentation, which is linked here in the downloaded PDF, details the options for how to specify a dimension along which to add elements. Using a 1 indicates the sum elements along each column. This will result in a 1 by n row vector. Using a 2 indicates to sum elements along each row. This will result in an m by 1 column vector. And then using the word all indicates to sum all elements in an entire array. This will result in a single scalar value. Therefore, the dimension 2 is desired for our case. Altogether, the new and improved dot product anonymous function is written as follows. The skeleton of the function remains the same, but then we use the sum command wrapped around a vectorized array multiplication between v1 and v2, and then we specify the argument 2 to indicate that the result should be summed along each row. To recap the capabilities of this function, it accepts two m×3 arrays as inputs. It then computes m dot products between each 1×3 row vector pair within the two inputs. And most importantly, it is extremely easy to read because it is so short. Now consider the following update to the earlier random array function to assist with generating large test arrays for our new dot product function. The original accepted a single scalar length to determine how long a randomized vector will be. This function accepts a size array. Then we can define two input arrays. v1 and v2 are both random number arrays with size 100×3. Now, both v1 and v2 are m×3 arrays where m is 100. These m×3 arrays can be tested in the fully vectorized form of the dot product function where v1 and v2 are again defined as randomized 100×3 arrays, and then the dot product values are computed by passing both v1 and v2 into the anonymous function. This produces a 100×1 vector output, where each element represents the dot product between the corresponding pair of vectors in the original two inputs. In summary, this lecture covered that vectorization is the ability for code to execute a single operation on a whole set of data at the same time. Vectorization enables large problems to be solved more quickly and in a much more visually clean manner, which simplifies the code for comprehension and for debugging. For addition and subtraction, no modification is required of the operator, but for multiplication, division, and exponentiation, they require the addition of a preceding period to indicate a vectorized array operation. In the previous lecture, we wrote a custom function to take the dot product between two vectors. Now we use the directional sum command and element-wise vectorized multiplication to solve the dot product for many pairs of vectors.